So I don't know, that's a new feature I don't like. We are going to be done around a little bit before 2:30 today. And then I'll be available on Sunday, and then we'll do our discussion again on the discussion board. So make sure you post there. All right, so this week we're talking about, make sure I'm sharing the right screen, time series data and forecasting. And in terms of technical concepts, we're not going to cover any new ground. We will talk about some different ways to fit regression, like basically the same trend line regression fitting we've done for other data. It's just that now we have a time component, a variable, that's all. We will talk about different types of seasonality and some different tests that one can run. My goal for you is to understand this section of analysis, understand how it might be applied in the field, that there are different ways of seeing correlations in time data. But then when it comes to your exercises, you're just doing some very simple manipulation, just plotting data and fitting a trend line, nothing crazy. We're not gonna do any of the more advanced statistical tests to check for like autocorrelation or anything. I do want you to understand the concepts, but as far as application goes, I think you'll find that it's pretty straightforward this week. So, all right, so forecasting is actually very difficult. We use it all the time. I use it for economic analysis. The FAA has to publish inflation rates for labor for federal employees, and then also pull from the Bureau of Labor Statistics. They have to extrapolate inflation rates for labor in different industries. We use it for like resource planning, trying to figure out, so other companies would use it to figure out staffing demand, which might have a seasonality component to it, and then production schedules, and then there's this whole financial sector as well, like stocks and bonds and things of that nature that are that tend to be correlated to their past points in time. So we're looking for patterns or relationships in historical data, and then we're extrapolating from that a pattern to predict a future value. The reason this is difficult is because time series data is often very noisy. If you try to zoom into like if you're looking at annual data, it might be pretty smooth. You might see this nice, clean kind of linear trend. But if you move into months, your data might start looking up and down a little bit, but you still see that big trend. And then if you zoom into daily, you might have so much noise that you can't see the trend and you've lost it completely. So we're trying to separate out this noise, this random behavior that comes with a time variable from the underlying pattern. And sometimes those patterns need to be part of our prediction, which adds another layer of complexity. There's also, there's also so many things depending on what you're doing. If you're in the financial sector, there's no guarantee that the future is going to be anything like what we predict. So many other external factors can alter the course of history and the future that we can make predictions, but they may not come true. So we have a lot of assumptions that go along with forecasting that have to be documented and noted as well. Okay, so extrapolation models are quantitative models that use past data of a time series variable to forecast future values of that variable. The ones that we're going to talk about are just regression, autoregression, moving averages, and exponential smoothing. We can do all of those things in Excel, either the old-fashioned way with formulas and charts, or using the stat tools add-in. And this is probably a great time, if you haven't played with it, to learn how to use it, because moving averages and exponential smoothing are easier on stat tools. Also, you could, and we don't need to do it for our homework, but you could pull time series data into Tableau and do moving averages very easily. Tableau and exponential smoothing. Tableau has those functions built in native as well. So if you find yourself down the road needing to do it, you could consider that as well. All of these methods, though, the whole point is they're looking for patterns and then they're guessing about the future. And when it comes to time series data, simple is usually better. Complex models tend to be overly fitted for the historical data, and then there's too much noise. So basically, if you have a very complex model with a time variable, you're fitting the model to the noise instead of the pattern when you start to get too complex of a model. Econometric models are also causal or regression-based models. Use regression to forecast a time series variable by adding in other explanatory time series variables. We do not get into this mathematically. This gets very complicated. We have like lags for the regression equation, whether they're dependent or explanatory variables. We have autocorrelation going on and cross correlation and all these kinds of things. So mathematically, this becomes a nightmare, and we're just gonna basically skip right over that. We can also combine forecasts into a final forecast. So if we have different forecasting methods, the errors from each of those might cancel each other out. And so by splitting them into two different models, we can kind of prevent some of those issues. And then it gives us the ability to do general types or different types of forecasts. And how many to combine and how to weight them is like a whole field, but it can be done, and just to be aware of that methodology. All right, so what does time series data look like? If an observation has a trend of either increasing or decreasing regularly through time, then we say it has a trend. It can be linear, as in A here. So the observation is increasing or decreasing by the same amount from each period, each time period. Exponential trends occur when they increase at a tremendous rate, an exponential rate, from period to period. And then S-shaped trends can occur where it takes a while for things to start increasing, then it rapidly increases, then it tapers off to a fairly constant level. That's this graph here. If we have seasonality, our data, this is what we're kind of more familiar with when we think of time series data, is time series data with seasonality. So the same seasonal pattern repeats itself year after year. So there's still maybe, this is just seasonal data with no trend, and then B shows seasonal component, but there's still an upward trend. Cyclical components are usually, so the data is affected by some kind of business cycle. These can be harder to predict than seasonal because seasonal variation is usually more regular. Business cycles can vary. So depending on what's driving the cyclical nature of the data, it may not be consistent for those cycles. So we know a seasonal cycle is a year long, but a business cycle could be longer than a year and may not be the same from period to period. Then we get noise, just random variation. It gives that this irregular shape. So we have our trend, our seasonal or cyclical component, and then everything else is out of our control. So if it's financial stuff, there's other things that influence the stock market besides just what people are buying and selling in the recent past. And things like oil futures, even, no one's expecting that there will be a cybersecurity attack that will shut down production. So those types of things we just can't predict, and they create random noise or conflict, other things like that. For like staffing data, a pandemic can completely alter what our data looks like. A really bad flu season, a downturn in the economy, different things can create noise in the data. So this creates a lot of unpredictability with time variables that we don't see with other variables. We're not going to do these calculations. Don't stress too much about the formulas that they're showing you, but we just like we measure the accuracy of regression when we do that, we can measure the accuracy of our forecasting, and we calculate forecast error. And it's the difference between the actual value and what we forecasted. And the three major things that they calculate for error: the mean absolute error, the root mean square error, and the mean absolute percentage error. These are all similar to the types of errors that we measure for regression. They're just a little bit different because the error related to the forecasting data is a little bit different. We generally use software packages to calculate these things, and they will choose for us the best model that minimizes these errors. So with regression, we were minimizing the least squared error. Here we're minimizing one of these three error terms. But we're still only guaranteeing that we are fitting a model well to our historical data. There's no promise that it's going to fit future data well. And unlike regression equations, our forecast errors don't always average to zero, like the residuals do from the regression equation. So if the average of our forecast errors is negative, we have a bias. Our forecast is overly optimistic. And if it's positive, then our forecast is overly pessimistic, it's too low. All forecasting models have this general form. The fitted value is the part that's calculated from past data, and the residual is the forecast error. The fitted value includes all components of the original series that can possibly be forecast, and then the leftover residuals are that unpredictable noise. The best way to figure out whether a time series of residuals is random noise is to just look at the graphs visually. These are some common non-random patterns. And then, yeah, so you can see like there's clearly some things, going on with these data. There's another test called the runs test, which can be used to test for randomness. It's kind of our way of doing hypothesis testing for randomness with time series data. So we choose a base value, which usually is the average value of the series. Sometimes it could be the median. Then a run is defined as a consecutive series of observations that remain on one side of this level. So if we have too many runs or too few, then we can reject the null hypothesis of randomness. So let's actually just take a look at what all that means. This one is using which file? Stereo sales. Here we go. Okay, so this is the data. We have this monthly data, we have the sales data. They calculated the residuals, and then they did 3 different lags. And so the residual, they basically, to get the residual, they just took the average of all these values and then subtracted it from the value. So this is the sales minus the average of all the sales data. So you're basically just shifting this data here down to the average, and then you get your residuals. So we're trying to figure out, and these are zoomed in, that's why they look a little different, but we're trying to figure out if this is just random noise or not. So what they did here is they took, okay, so they're checking to see whether or not each residual is above or below So they pulled this residual information over here. And then if you wanted to use this yourself, you would just copy your data into the residuals here. And then you would set your cutoff value, which for us is 0. Okay, so the number of observed runs is right here. And there's 20. And then, so these are the runs that are above or below the cutoff value of 0. This value here, which is the average of the residuals. The number of runs expected under an assumption of randomness is going to be right here. And this is calculated from a probability argument that the book doesn't get into. So we're saying that this series of residuals has too few because it should be about 25 and we're at 20. Meaning that positive values tend to follow positive values and negative values tend to follow negative values. So the Z value here tells us how many standard errors the observed number of runs is below the expected number of runs. And then the corresponding p-value tells us whether or not that Z value is significant. And in this case, it's not. So we can reasonably conclude in this case that the residuals do represent noise. So you could replace this data and run the same thing. The point being here, though, is that there is a mathematical way to figure out if your data is random noise or not. Okay, so many time series follow a long-term trend minus that random variation, and it can be upward or downward. But using a regression equation is the easiest way to model this trend, and we can use the y sub t, where t is time, as our single explanatory variable. So the two most frequently used models for time series data is a linear or an exponential trend. Linear, that equation should look familiar to you. Y equals ax plus b, basically, in this case, a plus a is our b instead. So our intercept, and then our b times the time variable, and then, so b is our coefficient, and then some error term. The interpretation of the coefficient b is that it represents the expected change in the series from one period to the next. So if b is positive, it's an upward trend. If it's negative, it's a downward trend. The intercept term a is not as important. It's just what we expect the value to be at time equals 0. But what we really care about is how much during each time period are we increasing. So we can look at a graph and that will tell us whether or not we should fit a linear trend, really just by visual inspection. So here's our population data, and it's, pretty clear a linear fit's going to be good here. There's some, you can see it's not a perfectly straight line, but it's very close. So this just becomes clear. Yes, we should fit a linear trend to it. And if we do that, we get an R squared of 0.9974. I mean, that's really basically as good as it gets for using our actual data. So the population for the US is very predictable using a linear equation. Interestingly, if we look at the error, we see that it's meandering a bit from positive to negative, but it kind of zeroes itself out. This is clearly not random, but we're not going to do much better than a linear trend regardless. So it's just something interesting to note. It kind of implies that there's an autocorrelation or something going on here with the data, but it's okay. This is still an excellent fit for this model. We look at this, linear is going to be the way to go. An exponential trend is appropriate when the time series changes by, instead of a constant amount, a constant percentage each period. And so we would have had this similar equation, but now we have this multiplicative error term thrown in there, U sub t. So the equation is not that useful for estimating. We need the linear form for it, and we can do that by taking the natural log, so of both sides. So if we do that, we get that this natural log of y is equal to a plus bt plus the error term. So now we can do something with this. The coefficient in here, b, is expressed as a percentage, so it's the approximately the percent change per period. So if b were equal to 0.05, then we're saying about every period our value increases for that variable by about 5%. 1 second, sorry. All right, so if we do have a linear trend, then our plot of our natural logs or our logarithms would be approximately linear. So let's go to so when we look at this data here, we can see it's not linear, but there's potential for an exponential trend. So if we did take the log and plotted those, now we see that there is a linear trend. And I'm going to look for the R-squared. It's a pretty good fit, actually, 0.98. And these are just plotted the sales amount per time period. So nothing fancy. But that allows us to use that regression. And then they do a transformation of this data to get the final equation, which is here. The forecast sales equals 62.188 e to the 0.0654 t, and then that's how they got this graph. So the estimation period is right here where they fit the data to, and then this is the forecast. You can see as time goes on, though, that it's not such a great fit anymore. The exponential forecast is a little too aggressive. Okay, so now we're going to get into just a couple different kinds of models, just for your awareness, and so that when you look at visual inspection of time series, you can kind of get an idea for what might possibly be going on. So random walk models, the series itself is not random, but the differences, the changes from one period to a next are. So this is very typical of stock price data. If you need like an example in your mind of what that would look like. And the equation for a random walk model looks like this here. M is the mean difference. It's a constant, and then the noise term of error is here. And then there's a mean of 0 and a standard deviation that remains constant through time. A series that behaves according to random walk models has random differences. So if the series tends to trend upward when M is greater than 0 and downward when M is less than 0 by each period. So if you're standing in period T and you want to forecast the next period T plus 1, then you could use the forecast where you add this y sub t, and then this difference term. And they go into the difference term a little bit in the book, but the concept is more important. So if I'm standing in this time period, I've got to figure out where I'm going next, but it is complicated by the fact that my walk is now random. So sometimes I'm going positive and sometimes I'm going negative. Even though I have a general trend, I don't have a good sense of which direction I'm going to be going in any given moment. So that type of data looks like this. So we have this stock prices shown on the left. These are the closing prices for each month. And we can create a time series of the differences between each of them, and it would look like this. So this creates a naive forecasting model, meaning that the difference is practically zero. So you can see, like, here's the zero. They're kind of centered around zero. Another way to deal with data like this is to do a moving average. This would be the simplest way, and is used all the time. A moving average is an average of the observations of the past few periods where the number of terms in the average is called the span. So if the span is large, then extreme values are going to kind of be washed out and have little effect on the forecast, and we get this much smoother method for predicting. If the span is small, then we get less smoothing going on because those extreme observations will have a larger effect. So deciding on a span causes, it does require some judgment, and you can play with it. If you're in Tableau or you're using stat tools, you can kind of use some judgment and play with the span a little bit to get the right amount of smoothing, because you don't want to smooth so much that you lose your trend or that you lose your prediction accuracy, but you don't want to smooth so little that you you have too much noise still. So let's look at some data. For this is file. Okay, so we're going to go back to the housing data. Oh. I actually don't, I don't have this file. Okay. So it looks like they took some housing data and they tried to run some forecasting on it, and then graph the behavior. So the original data fitted with a forecast that's not smooth with a moving average is this red line. You can see, like, it's kind of all over the place. So and because they have a really low span, so they did exponential smoothing over, or moving average over the last 3 months. So if you plot that moving average over the last 3 months, you get still a lot of kind of a very noisy forecast. If they do a span of 12, so they take the moving average over the last year and they plot that, you get this line that's a lot smoother here. So this is a good example of how the spans affect your forecasting. Okay, so those are moving averages. For exponential smoothing, we're basing our forecast on a weighted average of past observations, and we place more weight on recent observations. So simple exponential smoothing works when there's no seasonality. If we have seasonality, we need to use Holt's method, or if there's, so simple exponential smoothing, if we have no pronounced trend or seasonality. Holt's if we have a trend but no seasonality, and then Winter's method if we have a series with seasonality that may also have a trend. So when you go into stat tools, you have these choices. You can run Winters or Holtz or simple. It's just a matter of knowing which one is appropriate. Every exponential model has at least one smoothing constant. It's always a number between 0 and 1. If we're doing simple exponential smoothing, there's one smoothing constant, which is denoted by alpha. We're not going to get too much into the math, but I just want you to see, so we can do this in stat tools. There's the directions are here, but this is what the forecast series looks like if we superimpose it on the original. So the red is the forecast and the blue is the houses sold. When there's a trend in the series, Holt's method has a way of mathematically dealing with it that adds some extra terms. That's all you need to know about that. Visually, so if you, we get better error measures. This is the same data. So the error measures are better. You can see the forecast and the houses sold are a little more in line with each other. But now we have a little bit more of a sensitive model. So we could run this again and tell stat tools to optimize the parameters, because right now this was run on the default parameters, and then it might be less sensitive. It might fit it a little bit better. But I just want you to pay attention to how these different methods give slightly different results. All right, so seasonal models. So seasonality is the consistent either month to month or quarter to quarter differences that occur every year. So if you think about like sales, you might have seasonality trends for summer and for different holidays that are very consistent year over year or month to month. So spring, fall, winter, summer trends, quarterly trends based on that, or like every Christmas and like, I guess if you're selling electronics, like around President's Day, there's like probably another spike when they do that big sale at the beginning of the year. So we can deal with seasonality by using Winters, the exponential smoothing. We can deseasonalize data, which we've sort of played around with in the past. And then you basically deseasonalize the data, do your forecasting, and then re-seasonalize it. Or we can do multiple regression and we can put in dummy variables for the seasons. An additive seasonal model is where we use a seasonal index and we just add it to the base forecast. So the indexes would typically average to 0. So we might plus up in the spring and summer and then plus down in the fall and winter. Multiplicative seasonal models, we multiply the base forecast by some seasonal index. So those indexes typically average to 1. The Winters exponential smoothing model is similar to Holt's mathematically, and that's all that you need to know. It's just slightly different. So let's look at the soft drink sales data. Actually, maybe because they were done in stat tools, but I don't know why. Let me zoom in here. Okay, so looking at this data, you can see that the seasonality is pretty consistent, pretty strong. That blue line, it's pretty obvious that there's something going on there. And by using the Winters exponential smoothing, it's not bad. It matches the seasonality pretty well. If we're deseasonalizing, one way to do it is called the ratio to moving averages method. So we basically just divide an observation by a seasonal index. And to figure out what that index is for that month, we would divide that month's observation by the average of the 12 months surrounding it. And so the small problem with that is that any one month is not in the middle of a 12-month sequence. So we compromise by averaging the two possible averages. So if we're looking at June, that would be January to December and then December to November. So we're just centering our month and from the 6 months prior and 6 months after. Then the usual way to combine all the indexes for a specific month then is to average them if we have several years of data. And then we had talked about dummy variables as well for the seasons. So depending on how the regression equation is written, we can create either additive or multiplicative. For quarterly data, that might look like 3 dummy variables for the first 3 quarters, and then we use quarter 4 as the reference, and then we estimate this equation. So the coefficients for the dummy variables would tell us how much each quarter differs from the reference quarter, and then the coefficient B here is the overall trend. We could do multiplicative, just letting you know we can do it. Not even going to touch the math on that one. So to do additive with dummy variables, it can be done in Excel by just creating those dummy variables. So this, and then running the regression output. So if you look at this table here, we see that we have these coefficients associated with the 3 quarters, and then our time variable and our constant. So it works. This method picks up the trend, and it's not the worst at forecasting. You see it's off a little bit here, and it's over a little bit up here, it's under a little bit down here, but overall it's pretty decent forecast. Okay, so as promised, there's really not a ton of content in chapter 12. It's more less technical and more about informing you different ways of managing this type of data and different ways of modeling it, handling seasonality and cyclical behavior. So if you look at the homework for this week, there's some conceptual questions, and then you're going to take some data and create a time series graph, and then just add a trend line and figure out which trend line is best suited for that data by eyeballing it, and then also by looking at the R-squared values when you do that. And then I want you to think about which trendline option is the best fit, and then if so, use that to forecast for the next 2 years. So use the regression equation and then just calculate out the time periods for the next 2 years. So when you open your data, which I will do here, there we go. And then same thing for the second. You're fitting just a couple different trends. And then you're going to look at the error term. So here's your data. When you go to do your forecasting, you need to do 2 more years. So, or right? 2 more years? Yeah. So just add your 2 years that are forecasted, and then you'll plot your data. You'll play around with these things here to figure out which one you want to use. And then you'll take the equation and you'll have to, whatever you do, you might have to pull out the coefficient. I wonder if it'll let me. That, and then there's also this term up here multiplied by the data point. I don't want these in scientific, so I'm going to do this. One of them is very small, which is why. Really small. Okay, maybe I do want this one in scientific. Oh yeah, negative 93, okay. Okay, so for my equation, I have this, and then I'm going to multiply it. I need the E times this times X, which in this case is 2018. So for my, that doesn't look right. All right, I'll have to play with this. But I'm plugging in 2018 for X here. So let's do it for the regression equation, just to keep things simple. Since I'm doing this right on the spot, I'm going to switch this over to linear. Okay, so I'm taking 958.94 times X plus, or actually it looks like minus, this in number form. Okay, so that would be equals this, that times X. Is that, let's see, still weird. Huh, sorry guys. That is a minus, right? Yeah. Let me just play with this for a second. There's something going on with this term. Let's do this differently. Let's do okay. If you're getting weird So it was the regression equation when you add that trend line is just, it's rounding too much. So try doing it this way to get your intercept and your coefficient. And then because these are such big numbers, that makes a huge difference. So that's why I'm getting, you know, these weird values, because there's way too much rounding. So we're gonna actually, when you go to your homework, do not use the equation, actually run regression. So if you decide that exponential is the way to go, remember you have to, and you can look in the book to see how they do it, but you're gonna have to take the natural log and plot that. So if we did linear here though, which isn't technically the best fit, now we can use this information. So we have the intercept plus this times the time period. Still really low, but it looks better. I'll have to look at that. I'll get back to you guys on why, whatever, I must be doing it too fast, but it should calculate out by just getting your intercept and your coefficient from this. And it looks like this is a good equation. So, and then once we get this sorted out, which I'll figure this out before we meet for homework help, but you would just plot these additional points onto here to kind of see what the next 2 years of trends look like. Okay. This should be, this is gonna bug me. But that's the process. Okay. Yeah, I'll have to. I'll have to take a look at that. I'll get back to you guys. I'll either post an announcement or go through it during homework help, and then, or if one of you guys figures out why it's so low, that'd be great. Okay, but the process is the same for plotting data and then running regression on it, and then using that regression to predict for different values of X. It's just that instead of X, this time we're using T. Another thing we could do actually that this might be better. It may not change anything, but let's try it. We can label our time periods this way. And then it's going to be the same concept. So now we're just predicting for time period 35. So the intercept plus this times that, which, yeah, I'm sorry, you guys. I don't know why the regression equation isn't working. I'll get back to you, but at least we covered the process. So okay. Anyway, let's not spend any more time on that. The second file is just slightly different data, but the same concept. Okay, and then for your discussion board, we are talking about data visualization, and then we're talking about correlation and autocorrelation. So in your course content for this, now that we've covered a couple of different kinds of methods, there's a video here about storytelling with data. I think this ties on nicely to what we talked about last week with the BI tools and Tableau. And now that you've had a chance to play with those concepts, the video here is just a talk by Carol Knaflic, and she wrote this book, Storytelling with Data, which I think might actually be used in some of the other classes. And then there's this Teaching to See video that's really cool that came from Edward Tufte's website. And I want you guys to watch those videos and just kind of think about tying together the tools that you learned about to visualize data, and then these concepts of like what makes a good visualization. How do we tell a story with data, and tie that all together? So that will kind of wrap up that discussion on data visualization and help you guys tie together all of the modeling that we've talked about in the last couple of weeks with presenting our findings to an external audience. And I'm really excited. This in particular, this Teaching to See videos is really cool. So I hope you guys enjoy that. Let's talk for a minute about your final project too. So right now, all of the modules are available. I made module 10 available a little while ago for those of you that wanted to figure out what this was going to entail. It is technically due a week from next Thursday, so 2 weeks from now. One second before I finish this thought.